Hello, I'm Chris Farinetta, and I'm here today with Dr. Doug Witherspoon of Hyper-V Technologies. Doug, why don't we start out with explain to us what is the Slingatron?
Well, the Slingatron is a mechanical hypervelocity sling, if you will. Imagine the old style sling with a string that you would whirl a payload around and then you let go and go flying off. Well, you can only get a certain velocity out of that before that string breaks. The Slingatron gets around that problem by using a spiral-shaped steel track. And you can accelerate a payload on the inside of that spiral by giving it a gyrating hula hoop-like motion. And if you do that at, say, about 60 cycles per second, it's pretty fast. It's a blur. You can't really see it. And you time it correctly with the entrance of your payload at the beginning of this, then the payload will phase lock with the motion of that hula hoop-like action.
So it'll be in time.
It'll
You
be
say
in
phase
time
lock
with it.
it's in
Yeah.
time.
And the payload will think that it's always being accelerated by that motion of the steel
Gyration.
track. And it'll keep it accelerating until it comes out the end. And by doing that, you can theoretically get velocities that are many, many, many kilometers per second.
How much velocity do you need to get into orbit if you're launching off the surface of the Earth?
Okay, low Earth orbit, LEO, has a velocity of about 7.6 kilometers per second. So we're going to have to provide at least that amount of velocity to get into low Earth orbit, obviously. The amount that you're going to have to launch from your Slingatron is going to be about that same number. You don't want it to be too much larger than that because then the Slingatron gets kind of large, and you want to keep it as compact and small as you can. So you're probably going to launch around 6 to 7 kilometers per second. You'll lose a little bit of velocity going through the atmosphere, which only lasts for a few seconds actually. And then you'll need to make up a little bit of velocity just to circularize your orbit once you get up out of the atmosphere. So something between 6 and 7 kilometers per second is a kind of a comfortable number to be launching at.
And so if I hear you correctly, you're also saying that there might be a sweet spot as far as payload mass.
That's correct.
Slingatron size.
That's correct. You're always going to need just a little bit of a rocket, a kick motor to circularize your orbit.
Per stage.
Right. And you'll have to make up some of your losses through the atmosphere. And so if you decide you want to keep the Slingatron launcher as small as possible, you might launch it 6 kilometers per second. In which case you might need a little bit larger onboard rocket than you would if you launched it, say, 7 kilometers per second. It's not a big difference, but it's enough to make a difference in the size of the
And it's
Slingatron.
also, it makes a difference in G-load inside the Slingatron.
That's right. The smaller your Slingatron diameter is, the overall diameter is, and the faster you're going, the more your centripetal acceleration.
So the higher the G-load.
That's right. And so at 7 kilometers per second, you're typically, or 6 to 7 kilometers per second, you're going to see accelerations of tens of thousands of Gs at the time it launches. So it's substantial. You're not going to launch people or fragile satellites with that. Just bulk materials like water and fuel,
But it is,
and building materials in orbit.
it is possible to build electronics that can withstand those G levels.
Yes, you can. That's been done for decades, actually. And what you're going to have to do is learn how to repay. If you want to do a satellite, for instance, that's got functionality and things like that, you're going to have to learn how to design those to handle these kinds of accelerations. Not a trivial thing to do, but it is doable. Yeah.
So how much research has been done today? How many Slingatrons have been built today?
There have been 3 Slingatrons in the past. The first one was a tabletop model about this big that was used to demonstrate this hula hoop dynamics and to prove that you could phase lock the payload inside the hula hoop. The second one was a spiral shape that was again about a meter in diameter, and we'll have some pictures of those in a moment. And that allowed a small, it was kind of a BB, a large BB that could roll on the inside, and that proved that you could actually use the spiral shape to accelerate these payloads to, in this case, about 100 meters per second. The third one was a spiral that was about a meter in diameter. That was the Mark II, and that actually had a payload that was sliding on that inner surface.
It was a box.
It was a sled, really. It was
not a ball. But
not a ball. It was a sled, and there's a picture of it in the movie, and that slid along on that spiral at 100 meters a second. That's 224 miles per hour, sliding along this steel track.
And we have a video clip.
Yes,
of that.
yeah, and I imagine we're going to show that about now.
So tell everyone, and this is the important part, tell everyone what's our goal with this funding. What do we hope to achieve?
Well,
and where will it get us?
Yeah, what we want to do with this project is to demonstrate and prove the next step in Slingotron development. We ultimately want to launch things into orbit. But that's too big a step for right now. So we're going to take the first step in that direction. We're going to build a Slingotron that is 5 meters in diameter, about 15 feet. And we're going to design this thing so that it can launch 1 pound payloads to 1 kilometer per second.
Wow.
Now in the actual demo that we'll do at the end of this project, we're only going to work with 1/4 pound because we're going to be doing this in our lab, and 1 pound's too much.
But we have stretch goals, and
stretch goals would get us to the 1 pound payload at 1 kilometer per second, or even higher velocities if we got enough funding.
We need to move the machine outdoors.
We would need to move the machine outdoors.
To
we can only do the 1 kilometer per second inside our lab here.
With the 1/4 pound.
Right, right.
Well, great. So, we look forward to your support in this important project. Our goal here is to transform access to space. And we hope that you can be a part of it. And we also hope that you will be a part of our users forum, where we will discuss various missions and applications for using the Slingotron for gaining access to space and doing activity in space. Thank you.
Thank you.